Good morning, everybody, and welcome to the fourth session of the Attosecond workshop. I am Fernando Martin. I will chair this session, which has the contribution from three distinguished speakers. Laura Cattaneo, who is currently at the Max Planck Institute in Heidelberg, but certainly will present results about his previous life at ETH Zurich. Hans-Jakob Wörner, who is at ETH Zurich, and John Marangos from Imperial College. So every speaker has 30 minutes for the presentation. And after the presentation, there will be time for questions for around 10 minutes. So I encourage the audience to send their questions through the chat that is available in the platform. And if there is not enough time to ask all the questions that we'll receive, I encourage the participants to go to the Meet the Speakers session, in which you will have plenty of time to discuss with the speakers about whatever you want. So then I think we can start the session. And then I pass the word to Laura Cattaneo.
Good morning, everybody. So I'll start my presentation. And okay, so this morning I decided to indeed talk about under-result photoionization dynamics in simple molecules. And then I will present you two experimental cases, hydrogen and carbon monoxide. I would like to emphasize in the beginning why we need to access to angular result measurement to actually access information about photoionization time delays, especially in molecule case. So in fact, if we look at the definition of the observable that we look at when we perform photoionization time delays measurement, the so-called Wigner time delay, which is actually a differential phase accumulated by a free electron traveling across a certain distance with a fixed kinetic energy compared to the same phase accumulated to another electron traveling the same distance but subjected to a half scattering potential. This differential phase can be translated in a time unit by performing the first derivative with respect to energy, and it's the so-called Wigner time delay. So looking at such an isotropic case, it doesn't result important to have any information about the angular emission of the photoelectron. But when we come to look at, for example, the simplest molecule we can think about, hydrogen, it's a very complicated case. So here we are looking at the potential energy curves where we can access to many states, so a forest of states, and having access to the angular resolution, so the angular information of photoemission electron with respect to the molecular axis, will allow us to disentangle those quantum paths that we can access. Even more clear is actually the case for carbon monoxide. This has been a calculation performed by Holhoff in already 2016, where it's extremely clear. Here you can see the time delay already, which can be measured or could be measured by escaping, when an electron escapes to different angles with respect to the molecular axis, passing from extremely positive to extremely negative. And indeed, you can see that there is a direct correlation of the time delay with the angles at which this electron are escaping. So angular resolution is a key element to understand and to extract meaningful time delays from molecules. But is that true only for molecules? Well, it's actually been studied from the KER-E group already, also several molecular cases, atomic cases, like for example helium, where depending on the type of continuum that the electron will access as a final state, like in an S type of state or a this type of state, so the angular momentum, this will actually translate to a different time delay. As you see here, this is time delay versus emission angle. So this is also true for atoms, not only for heliums, but has been studied also for argon. Okay, let's move to a key element actually to access to this angular resolution from the technical point of view, from an experimental point of view. So beside the time resolution that we actually in ETH Zurich obtained by an attosecond front end, of course, combining an XUV pulse, either an attosecond pulse train or a single attosecond pulse in the range between 20 to 50 electron volts, since we normally generate from argon, combined with a normally long 30 femtosecond or 6 femtosecond IR pulse as a probe. The key element is the detection scheme, which has been performed by a cold target recoil ion momentum spectroscopy, in short, cold TRIMS or reaction microscope. The key point is that, beside the fact that we detect in coincidence for each photoionization process, the ion and the electron, we detect the 3D momenta with which each charge fragment is being emitted. So this means accessing to the angular information and the kinetic energy of all the fragments. And here comes my very simple outline. So the two experimental cases I would like to talk about. And in case I have still 2 minutes, I will give you a flavor of some more recent measurements. Let's start with hydrogen. And let's meet this molecule in this very nice potential energy curve, which is quite scary because, as you can see, we actually are photoionizing them with a combo of attosecond of harmonics, which actually are able to populate all these states. So this is really a nightmare when you want to disentangle all the paths and actually compare electrons which actually had different access to different states. Thanks God, we have the cross-section that already clean a little bit the situation, excluding all the states that are belonging to the two set of doubly excited states, Q1 and Q2. Then we have a second point that allows us to distinguish between non-dissociating reaction, meaning that the excess of energy absorbed by the XUV photon will become only kinetic energy release of electron, and we have simply an ion fragment which is H2 plus from dissociative photoionization reaction, where the energy of the XUV is shared between the electron and the ion, also called kinetic energy release, and the dissociation limit, of course. How we can distinguish between these two paths? Well, thanks to our detection, we can measure the time of flight and either select on H plus and H2 plus. But within this dissociative path, here we still have 4 states that we have to access. How we can distinguish between auto-ionizing state and not auto-ionizing state? Well, we need to access to the kinetic energy release. In fact, in the past, it has been already studied that by measuring it and separating photoionization reaction, ending up with a kinetic energy release below 1 eV or above 1 eV, we can distinguish between auto-ionizing and not auto-ionizing. And within the auto-ionizing states, we have still the Q1 and the Q2. How we can disentangle them? Well, knowing the relative orientation of the molecule at the moment of ionization, and this enters the angular resolution. In fact, Q1 state will be mainly populating when the molecule is parallel, Well, the Q2 when it's perpendicular. And in fact, this is exactly what we do, because we do not align the molecule. We simply select those molecules already aligned at the moment of ionization by accessing to the beta angle, which is the angle of the molecule with respect to the XUV polarization axis. So now we have these keys. So these are all the paths that we actually can access. We can distinguish them by knowing the kinetic energy release and the angle of the molecule. I just would like to highlight the fact that in order to compare with theory, we will just neglect the perpendicular part, although we'll present some results about it. But for comparison with theory, we will actually do it only for the parallel case. So now comes the first experimental results, where we actually show some correlation diagram. So where we put in correlation the ion energy versus the electron energy, and we clearly see that we have two regions, the low kinetic energy in both orientation, perpendicular and parallel. Well, here we mainly, the dynamics is dominated by non-autoionizing states, and while here is autoionizing states. In the low kinetic energy, moreover, it's quite clear that we have a structure, a double peak, which is induced by the so-called bond softening effect induced by the long IR pulse with which the hydrogen is interacting. To compare with theory, we will compare only with the parallel part here, and apart from the fact that we don't have the double structure at the bottom part because they use a very short IR pulse, the comparison results very nice, and I want to highlight the fact that this calculation has been performed by solving indeed the time domain Schrödinger equation, taking into account not only the electron-electron correlation, but also the electron-nuclear correlation, so including all the caveats. Up to now, I didn't actually introduce any time resolution. How I do it? Well, we actually use the so-called RABBITT technique, that stands for reconstruction of attosecond beating by interference of two photon transition, where we actually expose our target to a comb of harmonics, and actually we can observe as a function of the Pump-Probe delay a photoelectron spectrum, which will appear exactly in the signal you see highlighted here, a yield of electron with kinetic energy exactly the difference of the absorbed photon energy minus the ionization potential of the target under investigation. And due to the presence of also the IR field, our probe, a two photon transition will be allowed, either emission or absorption. And this will end up to an intermediate kinetic energy forming, since there are two quantum paths interfering, this signal will be oscillating and is called silent, sorry. And we integrate the signal within more or less 1 electron volt, and then we can feed it by a cosine function containing a phase. And the time information we want to access is encoded in this phase, or the so-called Wigner time delay, plus two other contributions, the Attosecond and the continuum, which are measurement induced. And I will actually explain you how to get rid of them in the next slide. In fact, here I'm showing you a simple fully integrated RABBITT in H2, meaning fully integrated in with considering all the kinetic energy release and all the orientation angle of the molecule. Afterwards, we can select on parallel and perpendicular orientation. So we have two different RABBITT, and within each orientation, we can further distinguish low kinetic energy release and high kinetic energy release. Very important point is that in RABBITT measurement, we cannot access to absolute time delay, but only relative time delay. So it means that we need to compare two sidebands because we don't have access to the time zero. So in doing so, we can compare, for example, two sidebands, one belonging to the KER integrated and one to the low KER photoionization processes, and perform the difference. reminding us the content of this or each of these total phases. This means that performing the difference, we cancel out automatically the aperture and isolate what we call the molecular or atomic delay. And here are the results for the perpendicular case. For the perpendicular case, the threshold to populate the doubly excited state is around 31 electron volt. And indeed, here we see a clear modulation, which is that is caused by the presence of this autoionized state. But below this, what we expect is a completely flat time delay or phase, or zero phase, because the two electrons that we are comparing are facing the same molecular potential. But this is not what we observe, and the only dynamic that is going on at those kinetic energies is the fact that the nuclei are not just passive player of the dynamics, but they are interacting, and the photoelectrons, while escaping, are feeling it. And the same happens also for the parallel case. Above the threshold, we have a clear modulation due to the doubly excited states, but we have also modulation at low kinetic energies. And here it is confirmed by a very nice agreement with the theory. In the perpendicular orientation, we have a much better resolution, statistics, so we could further narrow our selection in photoelectrons, and we could actually select over interval of 1 electron volt in kinetic energy release and analyze the phase of the psi bands by comparing always the integrated KER minus 1 EV KER. And here we can see a regular modulation, because this is the classic definition of the Wigner delay, and is actually changing as a function of the kinetic energy release. But moreover, we can do the other exercise. We fix the kinetic energy of the electrons within 0.7 eV, and then we actually observe a clear modulation on both sides, and we can create we can interpolate the points and create a full surface, a unique surface, which is everything but not flat at all. And if we translate in time delays, we can see that they span from -half plus half femtosecond, so they are significant delays. And within the dash line region, here the doubly excited states are not playing any role, and still the delays are modulated within ±200 attosecond due to the coupling with the nuclear motions. So I come with the first take-home message of this part, saying that indeed we observe a clear dependence of the extracted photoelectrons, not only as a function of the kinetic energy of the electrons themselves, but also the kinetic energy of the ions and the orientation of the molecules. So knowing the angular resolution, so accessing to the angular resolution is a fundamental element to understand the dynamics underlying in molecular processes, in photoionization processing molecules. And it brings us to highlight a new concept of the Wigner delay beyond his classical definition, to actually infer similar information about the dissociation dynamics or of the remaining cation. Okay, let's move to the second example, where we bring the angular resolution to a second step, because we needed to resolve not only the angular orientation of the molecule, but also the electrons direction. So let's recapitulate the observable for the atomic case. So this is clearly kind of isotropic, but namely, what if we actually face a molecule which has a non-isotropic potential, but for example, like carbon monoxide. And so we can think about a differential phase accumulated by two electrons traveling on opposite direction towards the oxygen and towards the carbon, and indeed define what we call stereo Wigner time delay, which was actually already mentioned or identified by Ciacconi in 2014 in a theoretical work. So that's exactly was our motivation. Can we access to this stereo Wigner time delay? Simply due to this asymmetry of the molecular potential. So that's exactly what we did, and we performed more or less the same step to disentangle all the states in this photoionization reaction. So we can access as usual to the direct and the dissociative one. Since we want to know the orientation of the molecule, we need to rely on dissociative reaction. And the most efficient one was the one generating C plus oxygen neutral and 1 electron, of course. And then we could actually access again, build the molecular frame from the laboratory frame and actually have access to the beta angle. So here I can actually show you even a polar plot of the yield of ions, or C plus ion as a function of this beta angle. And so we can select over the perpendicular and the parallel one. And here is the potential energy curves of CO, which is even more complicated than hydrogen, but looking at the correlation diagram, we can actually have, we were very happy to see that there were only few signals coming out. So in particular, these 3 regions that correspond to mainly 4 states. And here I highlight the dissociation limits of them. And so corresponding exactly to the 3 signals that we see here. And of course, they repeat for each harmonics here, because here we select only over one part of the electron energy. And we confirm these 4 states by looking at also the kinetic energy release, and in particular, the vibrational structure in the perpendicular and in the parallel case. So now, as I said, we bring the angular resolution to a next step, because in order to build a stereo Wigner time delay, we need to know the direction of the electron, if it is going to the carbon or towards the oxygen in the molecular frame. And that's what we did indeed. We could distinguish between left to right, or oxygen versus carbon, and build the relative RABBITT and compare sideband by sideband, generated always by the same couple of harmonics. And then again, if we remind us the content of each of these phases, we realize that performing in this case the difference, not only the XUV goes away, but being these 2 electrons exposed to the same XUV, where they are actually, and because they are at the same kinetic energy on top of that, we have exactly a pure difference between Wigner delays. And here are the results for the perpendicular case and the parallel case. And in order to understand something, why in the perpendicular case we see an almost 0 delay, while for the parallel case we see a very strong negative delays at low kinetic energies, we compare with 2 different theories, very different from each other. The first one is actually the time-dependent resolution in ionic state method, which actually treat fully quantum mechanically the ionization process, but is only an XUV only measurements, let's put it like that. So there is no IR involvement in this. While we also use another theory which resemble a little bit more our experiment, because it includes also the IR field. And both theories are actually agreeing with each other and explaining nicely the experiment too. So for the perpendicular case, we have an almost 0 delay, while for the parallel case, we have a tendency to go negative at low kinetic energy release. There is still a big discrepancy here, which is due to the fact that the theory consider a limited number of states that they were accessed. Most probably in the experiment, we were accessing many more states which were actually contributing negatively to these delays. But let's focus a little bit on this parallel case and try to understand what it means, what's the meaning of this negative delay at low kinetic energy release, which is the striking observation. So if we look at the Wigner functions, which is actually provides the coordinate and momentum representation of the electron wave packet at the instant of birth into the continuum for single states, we can see that we have a completely different behavior. So here is extremely asymmetric towards the carbon. Here, instead of for the D2 pi, is nicely symmetric. And here is actually towards the right. This state is actually not contributing to the dynamic, but I show you only for clarity. So, would actually be that the asymmetry in those Wigner function is actually connected to the strong negative delay we see in the parallel condition. But still, this asymmetry in the Wigner function could be actually caused by two things. Either the original motivation that actually started the entire work, so an asymmetry in the molecular potential. But we look into the dipole moment of each single state, and the two states that are contributing, comparing this, the parallel and the perpendicular orientation, the most dominating one, are actually, they have the same sign. So this is actually not a solution, it's not answering to our question. So then there is a next option, which actually is the most valid one, and it corresponds to the fact that is the electron initial localization at the instant of birth into the continuum, which is actually delocalized towards the carbon or the oxygen, depending on the dominant state into of the dynamics. And if we translate this information in a time delay, considering only the average momentum with respect to energy, so there is no information about the molecular potential here, we can translate the mean position, we can plot the mean position of the localization of the electron at the moment of birth into the continuum as a function of the electron energy. And as we can see here, each state has a different mean position, which can be translated via this formula into a different time delay. And since we are looking only at the parallel orientation, so only these two states are contributing, I simplify here the plots, and I put on top our experimental points, which are nicely agreeing and telling us a very nice conclusion, or an interesting conclusion, I would say, that this investigation in time delays bring us other information in terms of space. In fact, let me conclude saying that this stereo Wigner time delays connects us to a sub-angstrom spatial resolution about the localization of the electron at the instant birth into the continuum on top of the timing information. And this work has been a very nice benchmark for the development of theoretical models, emphasizing indeed the dependence of the time delays, again, on the angle of the molecule, on the orientation of the molecule with respect to the XUV, on the orientation of the electron with respect to the angular orientation on the molecular axis, and the kinetic energy release. So my main outline has been concluded, but if I have still a couple of minutes, so Fernando still didn't show up, so I would like to introduce you to recent results we wanted to explore, again in hydrogen. Why hydrogen? Because still a very interesting and only apparently simple molecule, but exploiting another technique, which is the Attosecond streaking. And again, also in this technique, the angular resolution is extremely important. Why Attosecond streaking in hydrogen? Because actually itself streaking would allow energy resolution in sampling the accumulated phase from the escaping electron wave packet, which is much finer, so able to capture eventual fast oscillating modulation. And we wanted also to compare these results with the RABBITT one and see if actually we could get more or less the same quantity.
2 minutes.
Okay, so we have actually, I don't want to go into the detail of the technique, in fact, because I have only 2 minutes, just to say that streaking has an extra challenge to face in order to extract the time information, which is hidden inside the dipole transition matrix element appearing in the formula describing this spectrum, yes. Which in fact, this extra challenge requires an algorithm to extract the time delays. So in the past, it has been actually developed many different reconstruction tools, but all of them were actually based on very strong approximation, not allowing a very accurate reconstruction. Lately, we actually could develop a new algorithm, in short ACDC, where we can access to the absolute dipole transition matrix element, assuming that we know the XUV and the IR. So we first use the neon spectrogram as a reference in order to extract the XUV and the IR, and then we use these two pulses that we extract to obtain the dipole transition matrix element in argon. And we could nicely reconstruct, for instance, the argon phase, the DTME, in short, the dipole transition matrix element of argon, and compare with the RABBITT measurement from another group. And we were confirming that our algorithm was actually reliable and enough accurate. And so we use it for comparing neon and hydrogen and extracting enough information from the molecule itself, again with relying on the possibility to access to the beta angle and considering only the parallel orientation to compare again with the same theory I expressed at the beginning of the talk. And here is the results. It will be very short. So these are the streaking reconstruction of the dipole phase of H plus as a function of the photon energy across the threshold for populating the Q1 state, as you remember. And here is the comparison with the theory, which is remarkably good. And again, we want to compare with RABBITT. And here is the RABBITT again for the parallel case, and also nicely agreeing. But these are the experiments. And what we end up understanding is that this discrepancy for the RABBITT is again due to the bone softening effect. Although we use a very mild IR intensity, but the fact that this 30 femtosecond is actually modifying the dynamics that is going on in H2. And in fact, this is confirmed by the selection of the kinetic energy release. And if we select in the low kinetic energy where the bone softening is extracting the most, we have an even higher discrepancy, while selecting on the high kinetic energy is actually coming to a better agreement also with the calculation and the streaking. And with that, I would like to conclude and thank all the people that allowed this work to be actually performed. In the first place, Professor Ursula Keller, and the still present Jakob Fuchs, PhD in the group of Ursi, and all the former members, especially Joanna Voss and Luca Pedrelli, and both theory groups that allowed this work to be actually concluded a very nice and interesting conclusion. And of course, I will leave you with a short summary, and I would like to thank you for your attention.
Thank you, Laura, for your very nice presentation. So we have now time for questions. I'm going to check if there are questions in the platform. I don't see any question yet. So maybe I could start it takes some time to write the question, so that's why.
Absolutely.
so I will start with a very general question. Okay, so in all the experiments you have shown, you use cold trims just to know about the orientation of the molecule. then in doing so, you are forced to look at the dissociative ionization channel. You need dissociation of the ion, which means that you are looking in general at a channel that is a minority channel. It's not the dominant channel. So my question as a theoretician is, okay, what is the main complication you wanted to align the molecules with another laser? Because if you align the molecules, you would have access, and you don't care about, Coltrans, you would have access to the orientation, and you would have access to the non-dissociative ionization channel, which is the dominant one in molecules. So could you comment on this? I'm curious to know why you don't do alignment, you or other experimentalists in this particular context.
It's simply because it's much more complicated. So already having a system that combines an Attosecond front end with a Coltrans detector is not a trivial work. So it seems kind of a simple pump probe setup where everybody does it, let's say, not in vacuum, in air, and it's actually easy to, it's not actually easy even thinking of a let's say, pulses experiment outside a vacuum chamber, but when you actually have to work in vacuum and align 3 pulses and have enough intensity. So first of all, you have to have in your lab a laser which provides, because everything has to be synchronous more or less. So either it comes from the same laser, which has enough intensity and short pulses to provide all you need. So first of all, because for alignment you don't need a very short pulse, but you need enough intensity still. It's not so trivial. So it's not that just a simple whatever pulse will actually be able to align the molecules. And on top of it, you need a very short pulse to generate harmonics and still have a probe available for it. So I would say from a technological point of view, the coincidence of all these elements is not so, let's say, frequent. I would say it doesn't exist yet. But it's just our technological limit, I would say. There is, I mean, this would be absolutely a direction to go in order to access to the non-dissociative part for molecules and have very good statistics.
Okay, thank you. Now the questions have arrived. So there is a question by Eric Manson. The question is, wouldn't the H2 bond softening issue be stronger with streaking than with RABBITT? Or what else differs?
Yeah, indeed. I mean, even though we had a very strong IR pulse, or not very strong, stronger, I would say, in a streaking experiment, independently with respect to a RABBITT experiment where we have rather weak one, because as I wrote, it was 10 to the 11 if, in the RABBITT that we actually used. The fact that it's so short, so only 6 femtoseconds, doesn't allow, the bond softening is an accumulation effect. It takes some time to build up. And 6 femtoseconds, I would say, is the edge to see some growing of this effect. In fact, I didn't show here a plot, but in, for example, in looking at the, let's say, the ion yield as a function of the pump probe delay, we could actually see a modification of the kinetic energy release exactly at the end of the streaking pulse, so at around 6 femtoseconds. It is exactly where the bond softening start to actually modify the kinetic energy of your ionic charge fragments. So then within 6 femtoseconds, you are pretty much safe, and bond softening has not enough time to build up yet. So you are actually bond softening. There is this time window is a bond softening free. Unfortunately, RABBITT, although is actually very mild, has 30 femtoseconds to build up, and is definitely modifying the dynamics going on there.
Okay, there was another question by Marius Lehmann that is about the same thing. It's about this streaking effect. So I think you answered already this in the previous question. So there is another one by Dominique Platzer. the question is, in the case of CO, is there a physical reason for the theoretical beta perpendicular not to be exactly 0?
For the theoretical work?
Yes, for the
The going down, well, I would attribute this to the fact that, again, so in order to actually perform this calculation in a complete way, sorry, not in a complete way, in a reasonable time, physical time, so like calculation time, they actually had to consider a limited amount of states taking into place, so dominating the dynamics. And in my opinion, so this actually limited or modified, could explain the discrepancy between the experiment, which is actually randomly fluctuating around 0, and the fact that instead both theories are already predicting a slightly going negative at low kinetic energy release. So this most probably is due to the fact that in the experiment we are exciting many more states than those that are considered in the theory, and so there is this actually slight disagreement for the perpendicular, but also in the parallel it actually is reflected the same, although in a strong way.
Okay, thank you. Well, there are more questions, but we don't have time. So I remind you that you can go on asking questions during the Meet the Speakers session just afterwards this session. So let's thank Laura again for the nice presentation and for answering all the questions. And let's move to the next speaker, who is Hans-Jakob Wörner from ETH Zurich. So Hans-Jakob.
Together this very nice meeting, and I would like also to thank Fernando and the other initiators of this attochemistry network. This is really a fantastic and very timely opportunity to bring together these research efforts. So in my talk today, I will focus on some quite recent results, for most of it about advancing the techniques of attosecond spectroscopy from the gas phase to the liquid phase. And the underlying motivation for this work is that most chemical and also biological processes take place in the liquid phase. Yet, of course, there is a considerable complexity gap to overcome in going from gas phase studies with attosecond time resolution towards the liquid phase. And so the roadmap that our research group has been following is to push the frontiers of what can be done in the gas phase, but at the same time advance towards the liquid phase with the eventual goal of studying molecules in solution. In addition to offering the natural environment to study molecules, this also offers a lot of new interesting scientific opportunities, especially in terms of moving from unimolecular reactions to bimolecular reactions that involve the transfer of charge and energy between the molecule and the solvent, or between different molecules in solution. And so the outline of my talk will be organized along this idea. In the first part, I will be covering the attosecond dynamics of ionization of water, covering gas phase, liquid phase, and small clusters. The method we use for this is photoelectron detection, but also photoelectron-photoion coincidence. And in the second part, I will be discussing attosecond charge migration with some very recent result on dephasing and revival of the process with the complementary technique of attosecond soft X-ray transient absorption. So why should we care at all about the ionization of water? There is a very fundamental reason, namely that most of radiation chemistry and radiation damage is actually initiated by the ionization of water. So the large fraction of damage caused to biological molecules and also chemical processes taking place are not initiated by ionizing radiation directly interacting with these molecules, but by ionizing water. And so in this first half of the talk, I will be completely focusing on this aspect. What can we learn about the ionization of water? And of course, this is a time scale. This is a process that has many different time scales. And very recently, we published a paper that was able for the first time to resolve all the steps on down to the few femtosecond time scale of this ionization of water. Most importantly, resolving the time scale of proton transfer following the ionization of water, but also looking at the thermalization and formation of the solvated electron and comparing the situation for excitation of ionization or ionization of water. But now, of course, this is an attochemistry conference, so I will in this talk completely focus on the attosecond time scale. So looking at the ionization event of water itself and trying to decompose this process into its most elementary quantum mechanical steps. So I will start by some relatively old work from 2016. This is a paper in which we reported the first measurements of time delays in molecular photoionization. And in this paper, we studied water in the gas phase. So this is a RABBITT measurement. The RABBITT technique has very nicely been introduced by Laura and also by Fernando Martin yesterday. So what you can see here is a RABBITT experiment performed on isolated water molecules, H2O, in the gas phase. And this measurement allows us to extract the time delay between photoelectrons that have left the ion in the ground state, X plus, or in the first excited state, A plus. And because of the high resolution, which allows us to separate every electronic state, we are able to extract a time delay between ionization to these two states of the ion. And here, in this particular case, we find a delay of 10 plus minus 5 attoseconds. We performed the same measurements also on N2O, again measuring the time delay between X and A. And in this case, we found a time delay of 35 attoseconds. These experiments were possible because we used a metal filter to spectrally filter the attosecond pulse train and reduce the number of harmonics, which allowed us to manage the spectral overlap in the relevant region. So this allows us to extract the time delay at a particular photon energy, and using other metallic filters, we were able to repeat the same measurement at higher photon energies, covering a wider range of photon energies. And in the case of H2O gas phase, we find very small delays, whereas in the case of N2O, we found large delays up to 160 attoseconds around the photon energy of 30 electron volts. And when we performed these measurements, there was no theory available to interpret them. So we developed our own theory. So Denica Baykusheva in my group developed a complete theory based on electron molecule scattering calculations, which allowed us to calculate these delays from first principles. And I will not discuss this formula in detail. I would just like to point out that one can calculate one photon Wigner delays based on this theory and plot them as a function of photon energy and emission angle. But what is important when comparing to experiment is to calculate the two photon delays or the two photon matrix elements. And then one can again plot them as a function of photon energy and emission angle in the molecular frame. And by comparing these two graphs, you can see that there is both a qualitative and a quantitative agreement between the overall maps of the time delays, but there are of course subtle differences which you can directly identify in these plots, and they come from the effect of the infrared field. And so when comparing experimental data, one should use these two photon delays or even more advanced ways to calculate these delays, as we have heard from Fernando yesterday. But for the moment, we will stick with this theory based on second order perturbation theory. And we can compare now the prediction after averaging over emission and orientation angles with the experiment. And we find very good agreement. So we can explain the very small time delays in the water monomer and the large local maximum in the case of N2O. Now, this large local maximum in the case of N2O originates from a shape resonance, which is accessed when an electron is ionized from HOMO-1 into the continuum. It populates this shape resonance state, which is trapped by the molecular potential to which one has to add the centrifugal potential. And this shape resonance in our calculation has a theory, has a lifetime of 110 attoseconds. And this 110 attosecond indeed is almost exactly the time delay that is predicted by theory. So these are two independent results from the same theory, but the time delay difference is equal to the lifetime of the shape resonance. And as you can see, this does not perfectly agree with the experiment, in which the delay amounts to 160 attoseconds. And so this shows that these type of measurements, they do indeed provide access to lifetimes of shape resonances, and that the theory is not yet perfect, but still needs some improvements. Now, this covers the topic of the gas phase, but I will now focus mainly on the liquid phase measurement. So this is a measurement that involves a liquid jet. So this is a stream of liquid water expanding into a high vacuum chamber, and we perform a RABBITT measurement on the liquid water and the gas phase that evaporates from this liquid jet at the same time. And this measurement now allows us to extract the time delay between photoemission from the gas phase and the liquid phase. So we repeat the same idea. So we use a thin filter to reduce the amount of high order harmonics, which are part of our attosecond pulse train. And then we can record a photoelectron spectrum. And this photoelectron spectrum now contains both liquid phase contributions, here shown in blue, and gas phase contributions, which are shown in orange. And because there is a slightly different binding energy for liquid phase and gas phase water, the two phases appear as separate peaks in the photoelectron spectrum, which allows us to separate them and identify them in order to extract the time delays. Now, as you saw in this photoelectron spectrum, there is, of course, complete overlap. And in order to deal with this overlap, we measured photoelectron spectra of gas phase water and liquid phase water with an XUV monochromator. So this is the measurement series. On the left, you can see the photoelectron spectra of gas phase water measured with each of the harmonics separately. And on the right-hand side, you can see the measurement of liquid phase water and gas phase water at the same time. And with these measurements, we now have the necessary information in order to decompose the RABBITT spectra of liquid and gas phase water by having a sufficiently small amount of unknown parameters, just the relative amplitudes of these different harmonics, in order to fit the RABBITT spectrogram. And so these are the experimental results recorded with two different filters, the tin filter and the titanium filter. And you can see here in blue the XUV only spectra that nicely show the resolved liquid phase and gas phase contributions, the XUV plus IR spectra. And then we study the difference spectra as a function of the XUV-IR time delay, which shows the expected RABBITT oscillation both in the liquid phase and in the gas phase. And now, in order to deal with this complete overlap between liquid phase and gas phase, we developed a new technique, which is described in this paper here, the complex valued principal component analysis, which allows us to extract phase shifts between completely overlapped RABBITT oscillations. And so what we do is we take the amplitude and the phase of the Fourier transform and we fit it in terms of the principal component spectra that we measured before. And this allows us to extract all the information contained in these spectra, as is shown here by the good agreement between the fit as the full line and the experimental data, which are the symbols. And so with this, we have the possibility now to extract the time delay between liquid phase and gas phase. We find that the time delays amount to 70 attoseconds at 21.7 electron volts, and about 50 attoseconds at 31 electron volts. So the positive sign means that photoemission from the liquid phase appears to be delayed compared to the gas phase. And in addition to this time delay, as you can see here, we also have a second observable, and this is the modulation depth of the RABBITT oscillations. Whereas the modulation depth is very high in the gas phase, as has been seen in many experiments, the modulation depth is considerably smaller in the liquid phase. And so, again, we had these results, but there was no theory around to interpret these results. And so we also started the development of the theoretical methods in order to understand these results. And so one can, as a very first rough overview, say when we compare photoionization from the gas phase and liquid phase, we have two main effects. We have the effect of the environment. So photoionization of this molecule will be different because the electronic structure has changed, but also because there is multiple scattering when the electron is emitted. And then as the electron is transported through the liquid phase, it can again scatter. And so there will be a possible effect of electron scattering on the time delays of photoemission from the liquid phase. And in order to understand this, we started from a very, very simple one-dimensional model where we employed the time-dependent Schrödinger equation to make sure there were no assumptions, no approximations made in the beginning. And we looked at the simplest case, what happens if we photoionize a model system and we allow it to scatter once on a repulsive potential, which is a qualitative model of scattering on a neighboring water molecule. So what we have in this system is a negative time delay from photoionization. It's about 45 attoseconds in our model system. And then we have a positive time delay, which comes from scattering on the repulsive perturber. And the classical expectation would be that we just have the sum of these two time delays, and we have a delay that is independent of the distance x0 between the two potentials. But it turns out the time-dependent Schrödinger equation gave a completely different answer, namely an oscillating time delay as a function of the separation between these two potentials. And so it took us some time and a lot of thoughts to understand this, but in the end, we were able to develop a complete analytical theory for this process and explain these oscillations. And so what these oscillations represent is the quantum mechanical interference between pathways that have interacted with the IR field at the point of ionization and pathways that have interacted with the IR field only at scattering. And so this is the result for a fixed separation being changed. But of course, in a liquid, one has a distribution of collision or path length distances defined by a mean free path. And so if one takes into account this exponential path length distribution and also takes into account multiple possible collisions, one finds this dependence. So for very short mean free paths, there is the classical limit is fulfilled. So the time delays are just a sum of ionization and n times the scattering delays. But with increasing mean free paths, these oscillations cancel each other such that for large mean free paths, all the scattering contributions disappear and only the ionization time delay survives. Now, this was already a first hint at what one could expect in these experiments. But of course, this was all very simple, one-dimensional. So we started the development of a three-dimensional model that includes all of these physics. This was done by Axel Schild, who is a junior theory group leader. And he developed this completely from scratch. So he developed a description of the laser-assisted photoelectric effect and laser-assisted electron scattering in 3 dimensions based on these earlier one-dimensional results. And he constructed a complete Monte Carlo trajectory simulation program in order to simulate this process of attosecond interferometry. And I don't have time to go in details, but the important conclusion is that the time delay that arises from electron scattering in liquid water are very, very small. They are a few attoseconds, and they decrease as the starting point gets closer to the surface. And if one averages over all the starting points that are relevant for the experiment, one obtains a time delay of about 2 attoseconds. And so this is entirely negligible in our experiments compared to the measured time delays. And so what this leaves as a most likely contribution is the effect of solvation on the molecule. And this also, of course, we can calculate, because in the theory, we can now simulate time delays for isolated water molecules. These are the absolute time delays now. And we can add one solvation layer, and the result is clear. The time delays increase with the addition of this first solvation layer. And if we add a second solvation layer, the time delays increase again. And this is the largest cluster we can calculate at the moment. And here the time delays amount to 61 or 30 attoseconds between this large cluster and single water molecules. And this agrees very well with the experimental results. And so from this, we were able to conclude that the measured time delays that we have obtained, they mainly reflect the effect of solvation on water molecules. So this is on one hand an effect on the electronic structure of the water molecule, but also the effect of multiple scattering in the immediate environment of the water molecule. Now we had the second observable, which is the finite modulation contrast. And this is remarkably different at these two photon energies that are quite similar. And so this is also something we looked for an explanation. And indeed, what is very interesting about the structure of liquid water is that it is quite inhomogeneous. So whereas in ice, every water molecule is tetrahedrally coordinated, in liquid water, this is not the case. Many hydrogen bonds are broken. This is known from other studies using X-ray absorption spectroscopy, but also X-ray diffraction. And what is the most frequent distortion is that hydrogen bonds are broken by either being stretched, so longer than the typical 2.75 angstroms or O distance, or that they are broken by bending. And so we studied the effect of stretching and bending on the time delays, and we found that at 21.7 eV, there is indeed a very large variation of the time delays by about a factor of 2, which explains the small modulation depths, because the superposition of RABBITT oscillations with very different phase shifts reduce the modulation contrast. And at the higher photon energy, the variation is much less, only about 10 attoseconds, and here indeed the modulation contrast is higher. And so we believe, based on these results, that the dominant effect of reduced modulation contrast is due to the structural inhomogeneity of liquid water, but there is also a possible contribution from dephasing. So the electronic dephasing of in liquid water, and this is something that we are currently studying in more detail. Now, for more details about these results, I invite you to read this book chapter, Attosecond Dynamics in Liquids, that we contributed to a book that is edited by Kiyoshi Ueda, and this will appear on the archive in a few days. So here we deal not only with attosecond photoelectron spectroscopy, but also with high harmonic spectroscopy that I will not have time to cover. Now, these measurements in the liquid phase, they suggest that the main effect is due to the immediate environment of the water molecule. And so this is something that we wanted to study and understand in more detail. And so Xiaochun Gong in our group built a cold trim setup in order to perform these measurements in size-resolved water clusters. And he did really a very impressive job getting this experiment running within less than a year. And he was joined recently by Sayosha Heck, who also contributed very importantly to these results. So what we do in this measurement is we record the ions. So there is a time of flight spectrum of the water cluster beam showing different cluster sizes. And in coincidence with each of these cluster sizes, we can measure the coincident RABBITT trace. And in this way, we can associate time delays to each of these different cluster sizes. Now, as you can see, these clusters are protonated. And this is because there is fragmentation. But luckily, the fragmentation pathways are known and understood. And what happens is that after ionization of a water cluster of a given size, there is proton transfer and a single OH unit is lost. This is the dominant pathway, and so we can use this information in order to associate each of these fragments with its parent neutral cluster. And so this allows us to extract time delays. Now we reference everything to the RABBITT, the coincident RABBITT spectrum of H2O+, and this allows us to extract time delays for each of the clusters up to 6 water molecules. And so we use the same technique I described in the liquid phase measurement. We perform a complex valued principal component analysis, which allows us to extract the time delays in spite of the spectral overlap that is unavoidable in these systems. And so this is the result. As a function of increasing cluster size, we see that the time delays go up until the tetramer, and then they remain flat out to the hexamer. The symbols, the big symbols are the experiment for sideband 12, and the small symbols, the colored symbols, are the theory here now calculated for the most stable isomers of these different cluster sizes. Now, of course, the interesting question is, where does this variation come from? So why do the time delays increase, and then why do they saturate? And so we studied this for quite some time. We performed a lot of calculations, and the explanation in the end is surprisingly simple. So the increase of the time delay with cluster size is due to the fact that the electron hole is being delocalized over a larger and larger amount of molecules. So the systematic increase of the time delays with the amount of localization is directly visible from these results here. And then, of course, the question is, why does the time delay then not continue to increase? And this is very interesting also. So for the tetramer, the most stable isomer has S4 symmetry. So that means every molecule plays exactly the same role because of the high symmetry. And therefore also the electron hole is completely delocalized in these states. And if one adds a 5th water molecule, this symmetry is broken. The symmetry is lowered to C1, there is no symmetry element left. And the symmetry lowering forces the electron hole to now partially localize. So here the delocalization only involves 2 or 3 water molecules. And this is then remaining constant, this degree of localization, for all larger clusters. So hexamers, heptamers, octamers, all the clusters we calculated that have low symmetry, they show this localization of the electron hole. And so we can associate this saturation of the time delay with the localization of the electron hole induced by disorder in the system. And the solid state physicists among you will immediately recognize the analogy of this situation. Periodic solids, there is a delocalization of the electron wave function due to the translational symmetry. And this delocalization is lifted due to disorder in the system, which is known as Anderson localization. And this is exactly what is happening here. The highly symmetric water tetramer gives the largest time delays because of delocalization, and then disorder induced by additional water molecules cause the electron hole to delocalize. And so here we have a hint that, at least in water clusters, the attosecond time delays are a direct probe of disorder-induced hole localization. And of course, if this is true more generally, then this makes attosecond time delays a very valuable tool to also investigate effects like localization in solids and in many systems. Now, the final question to answer is this compatible with the liquid phase measurements? And so this is now sideband 14. And indeed, you can see also sideband 14 shows these trends. The delay go up, they saturate. Here, the error bar is a bit large in the experiment, but they smoothly, more or less smoothly connect with the liquid phase delay that we measured. And indeed, if the time delay is caused by electron hole localization in liquid water, this is what we would expect. And so there is agreement with on the interpretation level, and these smooth transitions between the small water clusters and the liquid water indeed supports our interpretation of the results in liquid water. Now, to the second part of my talk, I will switch from time delays in photoionization to charge migration, and I will switch also in the technique to the soft X-ray transient absorption.
You have 2 minutes, Hans-Jakob.
2 minutes, okay. Then I have to be fast. I will skip a few slides, and I will just discuss. I will just discuss one recent result, namely Attosecond transient absorption spectroscopy on silane. So this is a very, very recent result where we used a CEP stable pump pulse in order to initiate dynamics in the silane molecule, and then an Attosecond soft X-ray pulse to probe the dynamics. And so what is usually done in these experiments is that the IR field ionizes the molecule, and then one studies the dynamics of the ion. But what we found in these experiments is that this strong pump pulse also creates a superposition of electronic states of the molecule. And we are then probing this electronic superposition state between a valence state, the 4A1, and the lowest lying Rydberg state, the 3D, as it evolves as a function of time. And so these are the experimental results showing transient absorption measurements at the silicon L edge. And the most important features are the observation of a very fast beating with a period of about 1.3 femtoseconds at early times. This beating then dephases after about 10 femtoseconds, and it revives later around time delays of about 50 femtoseconds. And so what we observe here is the dephasing and revival of an attosecond electronic wave packet in the neutral silane molecule SiH4. And to convince you that this is the case, we perform here a Fourier transform of the ATAS map. And you can see here the coherences that I described. They are around 0.7 petahertz. And the lines, the dashed lines here, they are drawn as guide to the eye for the condition when the energy gap is equal to h over the period of the dynamics. And this allows us to identify here the mentioned 1.3 femtosecond wave packet, which now from this map we can identify which states contribute. The lower state here is the valence state, and the higher state here is the Rydberg state. And the substructure is due to spin orbit and vibrational interactions. Now, as you can see in this map, there is a second set of coherences here, and they originate from a dark state, which is being populated by non-adiabatic dynamics in the silane molecule. So the pump pulse creates a coherence between these two T2 bright states, the valence state and the Rydberg state, but the valence state populates a lower lying valence state, which also becomes visible as a beating at a slightly higher frequency. And we probe both of these wave packets by X-ray transient absorption at the silicon L edge. Now, of course, we looked for theory support in order to understand these results. And the theory support was provided to us by Alexander Kulev's group. So Nikolai Golubev and Victor Depré did a wonderful MCTDH calculation involving 15 electronic states and 4 vibrational modes. And this calculation very nicely reproduces the observations that we have made. So they agree with the fact that there is a dephasing at the early time due to nuclear motion, and there is a revival of this attosecond charge migration at around 50 femtoseconds, which is due to nuclear motion. And now we can, of course, from the theory then look for the explanation. What is the origin for this revival? Here you can see the experiment. The electronic coherence decays in agreement with experiment, with the theory, and then it revives at a later time as is also in very good agreement with theory. And so this is the dephasing. Here we have the revival. And the reason for dephasing and revival is due to mainly nuclear motion in the Rydberg state and non-adiabatic dynamics in the lower lying state, which lead to a separation of the wave packet in coordinate and momentum space, and which suppresses the coherence, and then at a later time the coherence revives. And now, based on the calculation and its agreement with theory, with the experiment, we can graphically represent the change in the density. So this is the electron density of the excited state as a function of time minus the ground state density. And so blue is depletion and red is positive amplitude. Here you can see the silane molecule. And what you can see is the amplitude of this wave packet, this electronic wave packet, decreases as a function of time. So the movie covers the first 5 femtoseconds so far, and it plays over and over again. And so at early delays, you can see the large amount of charge migration due to the electronic coherence being large. And then you can see how this coherence decays as a function of time due to nuclear motion. And at a later time, it will revive, but this is not shown in this movie yet. So what is interesting in this context is this was a full quantum dynamical treatment of the nuclear motion. And there are actually calculations in the literature which allow us to compare the effect of doing a full quantum treatment of nuclear dynamics and doing the Ehrenfest treatment of molecular dynamics. So this is an example on iodoacetylene. And in the case of iodoacetylene, using the Ehrenfest method, it was predicted that the charge migration would survive for more than 30 femtoseconds without decay of the electronic coherence. But a more recent calculation that treated the nuclear dynamics fully quantum mechanically predicted this kind of dephasing and then revival of the electronic coherence that we have now observed in the silane molecule. And this shows that it is very important to use a quantum treatment of the nuclear dynamics in order to account for possible dephasing effects, at least in cases like this molecule, iodoacetylene, but also silane, where different electronic states are populated and the wave packets move in different direction in coordinate space, losing overlap. This is an effect that is not accounted for in the Ehrenfest dynamics. And so this is an interesting observation, I think, and also an interesting message for what to pay attention for in these calculations. So with this, I think I'm really out of time. So I would like to conclude by thanking all the people who did the work in my group, but especially also the collaborators who contributed to the experiment and also the theory, lots of calculations and discussions. And I would like to thank you all for your attention.
Thank you very much, Hans Jakob, for this very nice talk. We have time for maybe 1 or 2 questions. So there are, let me see. Yes, we have a question by Marius Lehmann. No, sorry, I was confused. No, by Oleg Kornilov. Can the charged layer on the surface of the following liquid affect measured ionization delays?
Yes, this is an excellent question. And indeed, we have worked for quite some time on understanding charging effects in liquid water. And this has actually led us to revise the ionization potential of liquid water in a recent paper. And so in this paper that was published in JPC Letters this year, we describe what we do. So what we do is we choose a salt concentration first that lowers the electrokinetic charging to a minimum. This is typically 30 to 50 millimolar sodium chloride that we put in water. This minimizes the electrokinetic charging. And then in addition to this, we apply a tunable bias potential of typically 0.3 to 0.6 volts, which is determined in situ in order to compensate for remaining effects. And this allows us to cancel the charging effects at least completely as we currently can. And this was done in these experiments.
Okay, there is a question by Marius Lehmann. As this crucial aspect of experiment with liquid water, could you comment about technical aspects of liquid jet?
Sure. So this is a quite mature technology nowadays. So what it involves is essentially a simple quartz nozzle, a standard HPLC pump that is standard in chemistry laboratories, and a cold trap. So the most important thing is to freeze the liquid water in vacuum in order to maintain high vacuum. And then the benefit of this is that one has a stream of liquid water which over a distance of a few millimeters, typically 3 to 4 millimeters, is completely laminar before it breaks up in droplets. And in this laminar flow region, one can perform experiments on liquid water in almost its equilibrium condition, because simply the flow is sufficiently fast, about 100 meters per second, that the change to the structure of water has not really had time to occur yet, and the water is essentially equilibrated. But this is known from work by several people, Bernd Winter and Noe Suzuki, who have developed these techniques over years, since the early 2000s.
Okay, there are more questions, but unfortunately we don't have time, so we should move on. So I recommend participants to go to the Meet the Speakers session to ask their questions and to discuss their comments with Hans Jakob. So let's thank Hans Jakob again for this beautiful presentation. And now we move to John Marangos from Imperial College. So John, please, go ahead.
I hope you can see my screen. Maybe not. Can you hear me yet? Fernando, can you hear me?
Yes, I hear you and I can see your slides.
Perfect. Well, let me first of all thank Fernando and the Attochem team for organizing this meeting and for running this very interesting network. Let me begin by overviewing what I'm going to talk about. I'm going to talk about measuring chemical dynamics in the attosecond domain, which is really the broad topic of this conference. But I want to look at how things are advancing in terms of the measurement technology in both the domain of high harmonic generation based sources and also in the domain of XFELs. And I think we'll see a major advance in the XFEL domain over the next few years. And I want to introduce some of those steps that are already occurring. So I start by talking about HHG-based attosecond X-ray sources. And I'll give a particular example of a recent application of those to photophysics of organic semiconductors from our laboratory. And then I want to talk a little bit about XFEL-based ultra-fast measurements and a recent experiment where we looked at the whole dynamics in an innovalence ionized cation. And then look at very recent advances in XFEL-based attosecond sources and applications. So I guess we're all familiar with the idea and the concept of charge migration, the idea that if you create a superposition state of electronic states of atomic, molecular or condensed phase system, one will see some kind of coherent evolution, oscillatory charge motion and other such phenomena. And this is a very attractive picture and was one of the pictures that propelled attosecond science forward in its early days. But we are now learning that, as Hans Jakob had just alluded to, the coupling to the nuclear degree of freedom is essential and must always be incorporated. And so I completely agree with him that modern quantum techniques are now required, and we're working with Graham Worth and others in order to develop those in our own work. And I want to show an example of a slightly earlier method to take into account that nuclear coupling. Rather than looking at the nuclear dynamics alone, it also takes into account the intrinsic 0-point spread of the nuclear wave function and how that will affect essentially the two-state superposition of electronic energies, which of course are now spread, and that leads to a dephasing. And this work was done by Mike Robb and Morgan Bashir, who basically demonstrated in a simple small molecule, paraxylene, if you include those nuclear dynamic effects, that instead of getting beautiful oscillatory electron transfer kind of behavior within the molecule, electron charge migration behavior within the molecule, that quickly damps. So effectively the coherence damps very fast. And that can, I think, in simple systems, as Hans Jakob has demonstrated, eventually show revivals, or it can actually just damp away and really not ever revive. And so it's a system-dependent coupling, and therefore we need tools to understand how electronic and nuclear quantum dynamics can occur. And of course, in general, in chemical reactions, these occur in a highly correlated fashion. So we basically need measurement tools that can track not only the electronic states, but also give us information about the nuclear states as well, as much as is possible. And so our interest has been in developing X-ray photon sources for probing femtosecond to attosecond dynamics using time-resolved X-ray spectroscopy. And so Hans Jakob didn't introduce this topic because he didn't have time, but I'll briefly introduce that topic in a moment. But we have basically two options of light sources that allow us to make these measurements. The high harmonic generation based sources, which have been around for 20 years, generating isolated attosecond pulses, and the X-ray free electron laser based sources, which are now generating also attosecond domain isolated pulses. And I'll talk about that toward the end of the talk. But I'll start with high harmonic generation. But first, before that, let me just motivate why we want to do X-ray spectroscopy. So what I'm showing here is some old synchrotron data of carbon-based materials, in solid state materials, in different forms, ranging from diamond to solid cyclohexane to graphite to solid benzene. And if one looks at the absorption structure around the carbon K edge, one sees vast differences in that structure, reflecting the fact that you have different bonding, different electronic states, different bond lengths. And so one can interrogate that spectrum and learn about the structure of the material with some degree of insight. And so dividing this absorption spectrum up into different photon energy ranges, in the very high photon energy range, high above the absorption edge, one has the XF region where in principle you can retrieve local structure. You can also get local structure from some of the shape resonances in the above threshold states, and then you have a region in which you see the excited valence states, the bound states of the system, the Rydberg states, the other valence states, and then there's also a region in which the whole states will show up. And I imagine in the Silane experiment Hans just talked about, he was looking at some of those whole states which will pop up once you've ionized the valence region. So our interest is in high harmonic sources, X-ray sources, which can cover the interesting edges, the interesting K and L edges in common atomic systems. For instance, oxygen, nitrogen, and carbon K edges range from 540 eV to 285 eV, and chlorine, sulfur, and phosphorus L edges from 200 eV to 135 eV. And then there are other edges like the silicon example Hans Jakob just showed around 100 eV. And of course, this is work where high harmonic sources have been applied to XANEs, time-resolved XANEs, for a number of years. The first such experiment was an atomic version of the experiment Hans Jakob just talked about. So that was the work of Garking and the Leone group in 2011. And then more recently, both Hans Jakob and the Leone group have shown gas phase measurements using HHG-based transient absorption. Okay, so I'm going to talk a little bit now about the work that we've been developing in my lab, where we've developed an attosecond source in the soft X-ray range based around a C-phase stable OPA system. So basically, we use a commercial OPA. We take precautions to ensure we got CEP stability, and then we send that output of the OPA through a hollow core fiber to do cell phase modulation, generate a broad bandwidth, and that allows us, using fused silica wedges, to compress those pulses down to around 10 femtoseconds. So as an example shown here of a 7 femtosecond pulse generated that way. And we've done a number of experiments using this source, including the ones I'll show you now. So here are an example of what happens as you scan the carrier envelope face of your laser, on how that influences the harmonic spectrum. So first of all, it basically slices through the harmonic spectrum at different CE phase, have been stitched together in this plot. And so basically, one feature to point out is carbon contamination on the optics means that you do always get to know where your carbon K edge is in these apparatus. So you can see a strong absorption feature around 285 EV. But in this case, the spectrum runs out beyond the oxygen K edge. And what we see is, as we roll the CE phase, we see the cutoff shifting backward and forward systematically with CE phase, which is indicative of the fact that in this cutoff region, I hope you can see my pointer, in this cutoff region, you are generating isolated attosecond pulses. And so you can move the region in which you're generating those isolated attosecond pulses around in photon energy by adjusting the intensity of your laser, by adjusting the gas pressure and the focus position, and you can basically move that cutoff right the way across the water window from the carbon edge, or below the carbon edge, in fact, the sulfur L edge, all the way up to beyond the oxygen edge in the experiments we did. And we reported this a couple of years ago now, and this work was led by Alan Johnson, who is now working in ICFO in Barcelona. But just to indicate that these are useful sources, here is the first ever absorption spectrum taken with, it's a static absorption spectrum of the oxygen K edge in the Mylar film, taken using this HHG source. It was the first time I think the oxygen K edge had been measured with an HHG source, admittedly somewhat noisy because there are very few photons at the oxygen K edge, but one resolves the dominant features in the oxygen K edge spectrum in that material. Going down to the nitrogen K edge, where there are many more photons, you get really much nicer spectra, showing even the Rydberg series in this case, and this was a spectrum that was obtained in a matter of a few minutes just by integrating. So these are static Zane spectra recorded using HHG. So the ambition is to extend from static to time dependent, to do pump probe measurements. And the material we've become interested in is polythiophene, P3HT, which is an organic semiconductor and an important base material for a class of polymer photovoltaics. And so it has, we're able to fabricate this in thin films of about 100 nanometers in our lab using spin coating techniques. We have various groups around the college who are expert in this technology, and so have assisted us in developing it. And we're able to study the X-ray absorption of this system around the carbon K edge here and around the sulfur L edge, and we can resolve with high resolution the main features of those edges and interpret which states they're associated with. And in particular, one of the states that we're very interested in is this feature here, labeled pi star 1 or peak A. This corresponds to a state which is the upper state of this state is also the upper state of the exciton, which is implicated in the solar light capture process excited in this material. So around 600 nanometers, there's a sort of an absorption resonance associated with this exciton. So the challenge we set ourselves is, can we measure the effect on the X-ray spectrum of exciting this material at 600 nanometers. And so we set up our experiment to do this. So this experiment is currently being led by Dougie Garrett, but there were a number of generations of PhD students contributing to this, including Lucas Miskaitis and David Wood, and Mary Matthews is our new lecturer in the group who's also been heavily involved in this work. And so they put this system together, or a number of over years we put this system together. It's a system to allow us to do pump probe, HHG based X-ray spectroscopy. So the pump arm, in the pump arm, we place a third harmonic generation stage that allows us to generate 600 nanometer light from our initial 1800 nanometer few cycle pulse that comes in. The other arm, the probe arm, goes into an HHG generation system and generates our soft X-ray pulses. The beams are then combined at a whole mirror and brought together at the target using a toroidal mirror focusing. And then we analyze the transmitted spectrum beyond the target using a standard X-ray spectrometer. And we're able to show that our pulses are currently at 600 nanometers, are around 16 femtoseconds in duration, and our probe pulses are nominally below a femtosecond in duration. So we basically pump the material well, we can measure the unpumped spectrum. I showed some examples of that just earlier in the static spectrum. So this is a transmission spectrum at the sulfur L edge, showing what the spectrum looks like in the unpumped case. And then we can pump with our 600 nanometer pulse, and then we look at a very different spectrum after pumping. And initially, we got excited that we would be able to do a time-resolved experiment straight away just by unblocking and blocking the pump and changing the delay between pump and probe. But it turned out to be much more challenging than that, because anyone who's done solid state X-ray spectroscopy, particularly on thin film materials, knows that there are a number of issues you have to counter. One is damage, both by the probe pulse and by the pump pulse, and the other is thermal loading from the pump pulse. And in fact, thermal loading has a big effect on this. I won't go through the details of that today, but essentially it took us some time to find ways to ameliorate that problem sufficiently that we could make reliable X-ray absorption measurements. And so I want to show you now the outcome of that work. So this is a plot of the delta optical density, optical absorption of the material. This is a milli optical density change measurement. So basically we're looking at few percent changes from increased absorption to decreased absorption in this plot, and we basically are looking at a series of delays between the pump and the probe, correcting for these thermal effects. So essentially we see two dominant features that appear around T0. One is exactly at the edge, the A edge that was identified earlier, which is essentially a change, a small change in the edge position, we believe. And the second is a transient feature that appears below the edge. And the interpretation of that in a naive way is that this is associated with the hole that's formed when you make the exciton. So that's perhaps a little bit too naive and doesn't fully take into account the multi-electron physics of these things. But nevertheless, what we see is this transient feature doesn't live for very long. It lives for in the order of 10 to 20 femtoseconds and then quenches. And we think it may be quenching due to exciton-exciton interactions or induced recombinations, but we're still analyzing that. But let me tell you a little bit more about the data analysis so far. We obtain a good fit to the data from a three-component phenomenological model. So basically, we put in two photo-induced absorption features and one ground state depletion feature, and we basically managed to match those well to the data. At first of all, this is the match in the band of delays between 0 and 40 femtoseconds, just integrating over the whole data, and then this is the match in the band from 40 to 100 femtoseconds, and you can see a good agreement with that phenomenological model. And we're then able to extract the time dependencies of different features. This feature here, for instance, and this edge shift feature. And this is what the extracted behavior looks like. So the transient feature has a lifetime of around 20 femtoseconds. And we are able to confirm the instrument resolution is around 16 or 15 or 16 femtoseconds. And then the onset of the change on the edge is pretty abrupt also, and then it remains static for a long time. So essentially, these we're now trying to correlate to known behaviors of this material, and to do that we're talking to experts, Artem Bakulin, who's an expert on this material, and Thomas Penfold, who's a theoretician who is currently calculating, and we're getting some understanding of what states are implicated in this. That interpretation and modeling is ongoing, so I don't want to take too much about that. Instead, I should move on, and just as an end note to this section, add that we've also been looking at few femtosecond sources for pumping ultrafast dynamics, and in this case we've used Kagome fibers to generate 3 femtosecond, of the order of 3 femtosecond pulses in the deep UV. So this is work which was completed last year in the PhD of Chris Brahms, who's now moved to our collaborators in Heriot-Watt in the group of John Travers. But what's nice is just by changing the pressure in that Kagome fiber, you can adjust the wavelength of the generated pulse from 300 nanometers down to 225 nanometers in this case, in all cases preserving around a 3 femtosecond pulse duration. Okay, it's time for me to move on to the second part, which is about free electron lasers. Now, many of you are, I'm sure, familiar with the basic operating principle of a free electron laser, the self-amplified spontaneous emission process. So you basically come into an undulator with a relativistic electron bunch, and through this instability and the interaction with the undulator radiation, you lead to a density bunching within the bunch, a sub-bunching within the bunch, which leads to the coherent emission of bright X-rays. And that can lead to pulses of less than 10 femtosecond duration, relatively narrow spectral bandwidth, at least compared to a synchrotron, and on a wide tuning range across multiple KEVs. And that makes it extremely valuable for both X-ray scattering studies and X-ray spectroscopy studies, and an exceptional available brightness. So I'm going to talk about SASE experiments and also enhanced SASE experiments, which is where you can actually get essentially transform limited or close to transform limited attosecond pulses. So I'll say more about that toward the end. All of the experiments I'm going to talk about were performed at the LINEC Coherent Light Source, the LCLS, at Stanford, at the SLAC laboratory in Stanford, which is basically using the repurposed Stanford linear accelerator to drive a free electron laser. So over the last few years, we, in collaboration with groups in Stanford, in Japan, in Connecticut and other places, have done a number of experiments on looking at X-ray induced ultrafast isomerization, looking at ways to improve the diagnostics of these ultrafast pump probe X-ray pulses. So in this case, we're using an X-ray pump, X-ray probe strategy, generating 2 pulses of controllable delay, and then adjusting that delay in order to do our pump probe measurements. And actually diagnosing those pulses is tricky and requires a lot of diagnostics. And we've looked at ways to improve that using machine learning, and that's been pretty successful. And most recently, we worked with the Nora Berra's group on looking at the fragmentation of fullerene in an X-ray, a strong X-ray field, and understanding the dynamics of that. And that was published recently at the end of last year. What I want to talk about today, however, is something more towards this attosecond dynamics end, which is transient innovalence Hall states. And so this work the experiment was led by Tom Barolow, and the analysis was performed by a range of people. Some of the dominant important people's names are given here. Bridget Cooper did the theory along with Vitaly Averbuk. So basically we're looking at suddenly created superposition of inner valence Hall states in the cation of the molecule. In this case, the molecule is isopropanol. And we expect to see rapid evolution of this hole within the molecular frame, at least for some of those inner valence states. And so using ADC3 theory with fixed equilibrium nuclear with the nuclear geometry fixed at equilibrium, Bridget calculates what you expect from some of these different old Hall states. So some of the valence Hall states show basically no time dependence in the survival probability of the hole. They're static. They follow Koopman's behavior well. Others, like the 5/8 inner shell state, is open to Auger decay. So it shows a rapid Auger decay in sub-femtosecond time domain. But other states, the 6A and the 7A state in this case, show some much more interesting intermediate dynamics. So these inner valence states, in particular the 6A state, has a number of correlation satellites, and that leads to this initial fast decay followed by predictions of oscillatory behavior in the whole survival probability. So the rapid decay in oscillations is driven essentially by a frustrated Auger process closely related to the processes that drive charge migration. And then the 7A state has some sort of intermediate behavior and shows some decay, which we will explore further. Indeed, going back to the original point about the nuclear geometry and trying to understand how to incorporate the effect of the 0-point spread of the nuclear wave function, Bridget performed a series of calculations in which she looked at many different geometries around the equilibrium geometry, sampled them at the correct density according to the expected wave packet, nuclear wave packet, and was able to show that, for instance, for the 5A state, the result of that averaging, it changes almost nothing. Whereas for the 6A state, the one that originally showed oscillations, those oscillations are damped out rather fast. So although the initial exponential decay remains, the oscillations get damped out, and that is an example of what can happen. It doesn't always happen that they damp out, but it really is very system dependent. And to understand the dynamics, you need to sort of start to go through processes like this in order to compare to your measurements. And then the 7A state shows also fast exponential decay, but it remains partially present even at long times. So our initial experiments on this actually used our HHG source. We used a version of our HHG source, driven by an 800 nanometer C phase stable laser to generate XUV attosecond pulses at around 20 EV. And these were used to ionize, to create the Hall states, and then were probed using an XUV-IR strategy, so similar to the strategy used by Francesca and others to look at whole states and charge migration in small gas phase molecules. We looked, in fact, at the signature of the kinetic energy release of the ion yield, and that showed a rapid decay, which we track to the fact that some of these inner valence Hall states can then be further photoionized by the IR field to lead to a Coulomb explosion, and only while they are undecayed can that process happen. And so basically this is sort of a map of the survival probability of those Hall states. But we want to know more, and what we really want to do is to be able to individually interrogate individual Hall states. So we'd like to look at the Hall states one by one, and so we want to adopt, or we've adopted, an X-ray pump, X-ray probe strategy. So the X-ray pump creates the holes, and the X-ray probe, tuned resonantly to the resonance between the 1s oxygen state and the specific hole, then it probes the state. So we're using a sort of X-ray absorption strategy, except rather than looking at the absorption of the photons, we look at the activation of the Auger electrons following the excitation of a 1s oxygen hole. So it's those electrons at the signature that we measure in these experiments. So the experiment was performed at the LCLS AMO end station a couple of years back now, or a year, so it's taken a long time to do the data analysis. We look at the electrons using a hemispherical analyzer. We measure the X-rays in both the pump and the probe pulse, on every pulse, because we have to look at all the fluctuating conditions and bin our data very carefully in order to extract meaningful data. And that's what takes so long. So here's an example of how we've looked at that data. So the intrinsic Sasse fluctuations allow us to actually change our probe energy over a range of different photon energies. So this actually allows us in the red region here to probe the 6A hole, and in the blue region to probe the 7A hole. So we can use that intrinsic Sasse fluctuation to actually extract data about both those holes independently and separately. And what we do then, so what we do is, first of all, looking at the 7A hole, it shows indeed an exponential decay. It's a fast exponential decay on the order of 15 femtoseconds or so. In contrast, the 6A state shows an even faster exponential decay, probably on the order of 5 femtoseconds, which is instrument limited. I mean, we have X-ray pulses in this case from the fresh slice mode that are of the order of about 5 femtoseconds.
John, 1 minute.
Okay, I'm going to overrun slightly, but let me go, and I will finish more or less on time. We also did an experiment with shorter X-ray pulses. So using the fresh slice Sasse mode, we were able to get the pulse durations down below 3 femtoseconds. And in this case, we see a much sharper rise and a fast fall. And unfortunately, we ran out of time, so couldn't complete this delay scan. But nevertheless, we can extract a very fast decay from this data. So the fast decay of the 6A state is consistent with what's predicted by theory. But what we'd really like to do is fully resolve these states and extend this measurement technique to more interesting situations where you might expect to see oscillations. And to do that, you really need sub-femtosecond pulses, because often these dynamics are just so fast. And that's what I want to conclude on by looking at the recent results on isolated attosecond X-ray pulses from XFELS. So this is work led by Argo Marinelli at SLAC. Not this first part. This first part was hard X-ray example. I'm just not going to talk about that. But in the soft X-ray range, the use of enhanced Sasse has enabled the demonstration of isolated attosecond X-ray pulses with gigawatt peak powers. And the method is basically about pre-modulating the electron bunch and then manipulating the phase space of the molecular bunch, so the electron bunch in a chicane, so that you create a very sharp temporal modulation in the lasable bunch density. And this leads to a sub-femtosecond lasing. And then you need to measure that you have a sub-femtosecond pulse, and that's done using an angular streaking technique with an IR field brought in to look at a sample ionized by the X-rays, in this case, a sample of gas or of small molecules. And so essentially one can then use the angular streaking method, the Atto clock method, if you like, to diagnose the pulse durations. And the pulse durations form something of a spread, but they're strongly peaked around 300 attoseconds. In this particular example, I think this was running at 905 EV, but they're tunable. You can go to 570 EV, and you get basically microjoule, tens of microjoule powers in isolated pulses, with pulse durations less than half a femtosecond, and a commensurate large coherent bandwidth in the pulses. And that large coherent bandwidth is very important for what I'm going to say at the very end. So first of all, these are really high brightness attosecond X-ray sources. So I've plotted here an additional point from the one that was actually plotted in the paper. I've plotted an additional point, which is the point from our work from 2018 on the HHG oxygen K-edge. And we're seeing that these pulses are 8 orders of magnitude higher power. And that opens up possibilities for non-linear X-ray interactions, as well as new forms of X-ray multidimensional spectroscopy. And as a taster to that, let me show you some very recently published results. So this was led by James Cryan, and we were part of the collaboration. And so basically, in the interaction region with these sub-femtosecond pulses, we have some nitric oxide, and in the nitric oxide, we're talking now about inducing a Raman, an impulsive Raman excitation, not of the usual nuclear states, vibrational states, but actually impulsive Raman of the electronic states. So the bandwidth of the pulse is large enough that you can create an impulsive Raman excitation of electronic states. And so we basically studied that through using a subsequent UV ionization pulse to measure the populations of excited states following the X-ray pulse. And we're able to confirm that this impulsive Raman process does indeed occur. And what we measured is in close agreement with what Antonio Picon's calculations show, which is the green curve. So we really have demonstrated the first X-ray impulsive Raman excitation using pulses with coherent bandwidth of around 5 eV. And that's the first step in doing new forms of pump probe spectroscopy that can track electronic excitations through material. So imagine we could do a two-color delayed impulsive Raman excitation at two different sites. You do say in this aminophenol molecule, which is one for a future planned experiment, you can excite, say, a wave packet at the nitrogen site and then probe that at the oxygen site some few femtoseconds later to see how the electronic coupling through the molecule is proceeding using these nonlinear techniques. Okay, and I'm going to conclude there. I thank you for your attention. The conclusions I think you've heard. I want to just flash up all the acknowledgements to both the team at Imperial College and our collaborators at SLAC and elsewhere. Let me just advertise very briefly a science case for a UK X-ray free electron laser. There's quite a lot about attosecond science in that as well. And if you're interested in finding out more about that, you can download the document at that link. So let me thank you for your attention, and I will conclude and stop sharing. Thank you.
Thank you very much, John, for this overview of the field and giving us the opportunity to learn so much about how to use these different ultra-fast sources. So now we have time for questions. Checking if we have received questions. Not yet, apparently. So as I said before, it takes some time to write the question. So I will start. So in the first part of your talk, you showed a slide in which you showed that you were able to produce UV pulses or visible pulses with 2-3 femtoseconds duration. So these are, I guess, single cycle or 2-cycle pulses at most.
Few cycles. Yeah. Remember, the cycle time is much faster in the UV. So.
Okay. So my question is: so do you expect that with these, if you use this as a pump and then you could achieve a sub-femtosecond time resolution when you
yeah, in principle, although we still haven't fully investigated whether these are CE phase stable. Because they're generated by a nonlinear interaction mechanism, a sort of dispersive wave mechanism, and there are, you know, in principle they should inherit the C phase stability of the drive pulse, but because it's a nonlinear interaction, small variations in intensity can lead to variations in the nonlinear propagation that can lead to small timing differences. And at the moment, I know that John Travers is considering doing some experiments to characterize that. I mean, it's clear that the jitter in timing is much less than the pulse envelope duration. So the question is it enough to establish CE phase stability? And that's now under investigation.
Okay, I'm checking the chat. Apparently there are no questions. So, well, I think then we can close the session here. And I want to thank all the speakers for being almost in time. I mean, this session is perfectly in time. And also I want to thank them for giving such exciting talks. I think we had a very great session. So thank you very much. And thank you, the audience, for being there. And I remind the participants that just after we close this session, you can go to the Meet the Speakers session where you can discuss with the three speakers of this morning. Thank you very much.